Hi, my name is Aaron Friedman. I'm a Partner Solutions Architect in Healthcare and Life Sciences at AWS, and I'm joined today by Jamie Kinney, who's a Principal Product Manager at AWS Batch. And we'll be talking to you today about how you can use AWS Batch and AWS Step Functions to design and run high-throughput workflows. So what we'll cover today, first is an overview of high-throughput workflows, and then we'll sort of give a general overview of our architecture. We'll then dive deep into sort of both services that are core to this architecture, which are AWS Batch and AWS Step Functions. And then we'll conclude by diving much deeper into the architecture. With that, I'd like to hand it off to my colleague, Jamie, to kick it off.
Thanks, Aaron. So I'd like to first start with a description of what we mean when we say high throughput workflows. So the diagram that you see on the left should be fairly familiar to folks. It's really common actually to run into work that you need to run within your organization, regardless of whether you're a university, a commercial institution, or a national lab. Typically, you have large amounts of data or input, maybe from an instrument or from some other source, that you need to first perform some pre-processing. And typically, this involves copying the data, maybe from an instrument into S3, and then maybe downloading it from S3 and performing some initial analysis. How big is this file? Is the file corrupted? What type is the file? Maybe extracting some metadata. And then it's common to proceed in your workflow to the actual meat of the workflow, the longest running portion of this job. And maybe that's a step that, instead of being network intensive, requires a fair bit of disk I/O, maybe a type of work that would run really well on the i3 instances that AWS offers. Or maybe it's a workload that requires large amounts of memory, as you might get from an X1 instance type. And then after you've performed your operation, you might want to do some analysis of the results of that large processing operation. Maybe this is work that's going to be GPU accelerated and taking advantage of MXNet or another deep learning library. Before you proceed to the final step of the workload, which might entail copying the results and some additional metadata to S3 or maybe to some of your databases. And once again, relying on a network optimized instance type to perform that operation before you finally conclude the workflow. And now, if you think about this, that's a lot of steps to go through. And the complexity is only increased when you need to multiply that times thousands or tens of thousands of inputs or even more. And so having a system that makes it easy for you to ensure that each step starts at the right time, that you run each of these steps on resources that are really optimized for the type of work that's being done so that you can gain compute and cost efficiencies as a result. Having a system that manages the concurrency of execution. If you have access to lots of compute, why not try to run all of these steps, or as many as possible, at the same time, instead of waiting for each to run sequentially? Also really handy to have a system that can manage the scaling of infrastructure, both up and down, as well as managing the diversity of instance types that are used. Error handling is incredibly important, as is providing notifications, letting people know when the aggregate of your work has completed successfully, or when individual steps in a given workflow for a given object might have failed. And then finally, having a system that makes it very easy to develop and extend and monitor the progress of these workflows can yield tremendous value to the organization. So this type of workflow that we've just described is really not endemic to just one vertical or one type of use case. This is actually really common. We see this, it's pervasive across all verticals. In media and entertainment, you have the conversion of file formats. Taking an input video file, for example, the likes of what Netflix might do. Take a large input file that's coming from a studio and converting it to formats and sizes and resolutions that are easily displayed on a 50-inch television and also on an iPhone or an Android device. You might have organizations like SmugMug, another AWS customer, who takes large collections of photos that are uploaded by their users and convert those into thumbnails and various resolution images that can be displayed on their users' websites. In the transportation and logistics space, you might want to do Monte Carlo simulations and analyze the transportation logs from various modes of transportation for products so that you can look for optimizations and also send reports back to the customers that are relying on you to ship their goods. In the life sciences, you have both genomics pipelines, but also computational chemistry, neuroscience, and other workloads that might entail processing data from genomic sequencers or high-resolution microscopes or other instruments. Manufacturing and design, if you're designing the next major mobile device or other forms of electronics, Oftentimes you want to look for efficiencies in the ultimate production of that device by simulating various electronic layouts and the use of various electric and chemical compounds to ensure that those devices are built as inexpensively as possible so that you can keep the cost to your end users very low. And so you'll oftentimes run through large batch processing workflows where you run various forms of simulation to get to the somewhat optimal design. In financial services, you do the same thing with ETL, data processing, fraud analysis, very common workflows. And in earth science and geospatial analytics, you have a need to take massive amounts of Earth observing data that are being collected by constellations of satellites orbiting our Earth. That data arriving eventually in S3 needs to be first processed and then converted into formats that are easily aligned with each other in a tile, and then overlaid with data that's coming from LiDAR and other sources of data that's collected here on Earth. Moving on to the architecture. So what we're going to describe over the course of today's webinar is an architecture that combines a number of AWS services to help you very easily define and then run these workflows and monitor their progression. And especially as we get to the latter half of our webinar, Aaron's going to describe how we've divided this architecture up into the workflow layer comprised of AWS Step Functions and Lambda, which are used to process objects that are written maybe to S3 or other systems and are triggered by calls to Amazon API Gateway. And then these workflows, various steps of these workflows, are executed using AWS Batch, which is used to scale up compute resources running on EC2 and running your applications, which are installed within container images that are stored within Amazon ECS Container Registry, or ECR, before results are finally written to Amazon S3 or various database systems offered by Amazon, or maybe a database that you choose to administer yourself. Now moving into the deep dive for AWS Batch. AWS Batch is a service that we launched at reInvent last year, and it's designed to help our customers run these types of batch processing workloads. It's the execution component to the architecture that we've just shown you. The goals of Batch were to help our customers, give our customers access to batch computing primitives, things like job queues and job submission APIs, instead of our customers having to deploy a combination of over a dozen different services that we were instructing them to assemble themselves previously. With AWS Batch, we offer a fully managed service that doesn't require you to install any software. Instead, you simply use our APIs, our web console, or CLI tool to create job queues and then submit jobs to those queues. And your jobs run on top of compute environments that we automatically scale for you. No need to launch instances or terminate those instances. We take care of that for you. Secondly, while AWS Batch looks an awful lot like batch scheduling systems that you might have seen for decades previously, we've taken this a step further by integrating AWS Batch with a number of other AWS services. Every one of the jobs that you run in AWS Batch has access to a job role that allows you to specify permissions at the job level so that your job can seamlessly and securely interact with services such as DynamoDB or Recognition or S3 or any other AWS service, all without having to embed your credentials within your job scripts, ultimately making it safer for you to run your batch workloads at scale and making it very easy for you to update your applications as you do things like rotate credentials. And then finally, a key goal of the AWS Batch service was to help our customers further reduce their costs when running batch workloads on AWS. So many customers were delighted by the opportunity to run batch workloads at scale. On AWS, of course, if you have 1,000 things that you need to run, there's no additional cost in running all of those at the same time. One instance running for 1,000 hours is just as expensive as 1,000 instances running for 1 hour on AWS. And so AWS Batch is designed not only to make that paradigm simpler, allowing our customers to run workloads at much larger scale concurrently where appropriate, but also helping our customers take advantage of low-cost EC2 spot instances and supporting things like automated job retries should you have a very aggressive bidding strategy and need to retry jobs that get moved from one host to another as a result of a spot termination. So now getting into the core concepts of AWS Batch. As I mentioned previously, Batch works by allowing you to submit jobs which are based on a job definition to a job queue. This queue is mapped to one or multiple compute environments, which are effectively rules that tell us how we can provision resources on your behalf. You tell us the size of those compute environments and the types of instances that we're able to launch for you. And then the AWS Batch scheduler is responsible for ensuring that those jobs are executed and run on resources that are provisioned as they're needed, based on the requirements of the jobs that you've submitted to AWS Batch. As a typical AWS Batch, you might see the following architecture. You might have an object that's written to S3. Maybe this is a genome that's coming off of a sequencer written into an S3 bucket. Maybe it's an image that's come from a satellite, or maybe it's a report or an input data set for a report that's part of an ETL pipeline. Your job is then triggered through a submission, either through step functions, as we'll show you today, or maybe directly through an AWS Lambda call in response to a CloudWatch event. Your job runs a command that's part of an application image, as you see in the job definition portion of the lower left-hand side of the screen. And your job could also have an identity and access management role. Once submitted to your queue, your job will transition from a submitted state to a runnable state. And then the scheduler for AWS Batch will ensure that if there are enough compute resources, we then create a container based on your container image on one of those compute resources using the resource, the CPU and memory requirements you specified. Because your job has an identity and access management role with permissions to interact with other AWS services, while it's running, it can read and write to S3, Dynamo, and other services. And then at the conclusion of your job, if you build this into your application, it can then write the output to the destination if you're choosing. Now I'd like to move on to a visual representation of AWS Batch. Okay, what I'd like to show you now is a collection of jobs. Now these jobs are part of a workflow, and you have a CPU-intensive job followed by two memory-intensive stages. The CPU-intensive jobs are the red jobs that you see. Red followed by two memory-intensive jobs that are green and blue. Within a vertical column, you have a workflow. And we have many workflows that could run concurrently. They're all independent of each other. But it's important that we don't start the green job until the red job is completed. And similarly, that we don't start the blue job until the green job is completed. Now, to run these workflows efficiently, we want to ensure that we run the compute-intensive workloads on an instance type that has a high CPU to memory ratio, and vice versa for the memory-intensive workloads. So the first step when you're going about this with AWS Batch is to define what we call a compute environment. In this case, we have an on-demand compute environment that has min vCPU set to 0 and max vCPU set to 360. And it also specifies instance types equals optimal. Let's look at each of these in a little bit more detail. What this means is that if you aren't using your compute environment, if you don't have any jobs that are ready to run, and therefore you don't need compute resources, this compute environment will scale down to 0 so that we don't incur any cost. If, on the other hand, you have a lot of work that's ready to run, we'll scale up to 360 vCPUs in this case, giving AWS Batch the ability to launch instances that have an aggregate of 360 vCPUs across all of the instance types that you've given us permission to launch. Because you've specified optimal, we'll be able to choose from any of the latest C, M, or R instance families to fulfill your request and get you resources to run your jobs. Once you have a compute environment, we can then define a job queue, in this case Q1, which will intend for high priority jobs. And we link your job queue to your on-demand compute environment. Then you can start submitting jobs to your job queue. Now, note that we have all of these jobs submitted to the job queue, even though there's interdependencies, in this case being managed by Batch. In other cases, these dependencies could be expressed in step functions, and the jobs being submitted one at a time. For this demo, we're going to show you jobs that are submitted all up front with Batch managing the interdependencies. And so because we want to run the compute-intensive workloads first, the first thing we're going to do is launch C4 instances. Now, Batch takes care of this for you, and we're actually running a couple of compute-intensive jobs concurrently on each of these instances. As the first of your compute-intensive jobs completes, we can then start launching memory-optimized instances, in this case, R3 instances. And as the first green jobs complete, we then use those same instances, which we've already launched, to run additional blue jobs and other green memory-intensive workloads. Now, at the same time, we've created another job queue, this time called Q2, which is mapped to a spot compute environment. And this compute environment is intended for low-priority workloads that are only worth running if they can run for less than a certain cost. In this case, when the spot market is less than 25% of the on-demand pricing. So in this case, we have the current spot price indicated by the pink arc that you see here, and our target price represented by this red line. At the moment, the spot price is a little bit higher than what we're willing to pay for this particular class of workload. But that doesn't prevent us from being able to tell Batch about the work that we want to run. So we can start submitting what you'll soon see as yellow CPU-intensive jobs to our low-priority queue. Now, as the spot price begins to fluctuate and eventually drops below the target price that we've specified, Batch will begin launching instances within the spot market for you. And we can start running your low-priority workloads. Now, the astute observer will notice that we're running these compute-intensive workloads for both the high priority and the low priority queue at the same time. What we really want to do is to run the high priority workloads before we take advantage of those compute resources to run our low priority jobs. And so what we're going to do to better align our compute resources to our business needs is to link up our high priority queue to our spot compute environment as well. Now we have jobs from the high priority queue running on both of our compute environments, and we've temporarily stopped submitting new jobs from our low priority queue to the spot compute environment. Once we finish all of our compute-intensive workloads in the high priority queue, then we can start turning off instances in our on-demand compute environment, and we can resume scheduling jobs from the low priority queue in our spot compute environment. And we'll see that in just a moment. Here we have the first of our compute instances in the on-demand compute environment that's no longer needed. So it's been terminated by Batch. Batch will hold on to it for the majority of the billing hour. So if there's opportunity to reuse that instance you paid for, we'll take advantage of that. But as there's no more work to run and we approach the end of the billing hour, quickly you'll see that Batch starts to scale down your compute environments until there's no more compute resources that are being used. Thus, when there's no work to run, there's no cost to using AWS Batch. So now I'd like to hand it off to Aaron to cover AWS Step Functions.
Thank you, Jamie. I always love seeing that video. It's one of my favorite animations that I think I've ever seen is AWS, either as a customer or beforehand or working here now. So anyways, I'd like to tell you a little bit about AWS Step Functions, which sits above AWS Batch in this architecture and really helps orchestrate the workflow. And like I just sort of said, Step Functions was designed to really make it easy for you to build distributed applications using these visual workflows. And what this looks like is you define your workflow itself in JSON in what we call Amazon States language. And this directly translates to the middle where in real time you can refresh your console and immediately see the new state machine pop up. You can see here, very simply things like branching states and other types of things as you build out, in this case, what looks to be a point of sale application. And then you can version and snapshot these state machines. And then when you're submitting executions against a specific state machine, you can actually monitor the path that the state machine takes. On the right, for example, you can see the path, and the green suggests that the individual states submitted successfully or completed successfully. So you can see this through this state machine, or perhaps you have a new execution that takes a different path, and you can monitor very specifically within a given execution and then track that as well in Amazon CloudWatch logs. Today, AWS Step Functions supports several different state types. The first is a task state, which is a single unit of work, and you can think of that as either an AWS Lambda function or an activity worker similar to Amazon's or AWS Simple Workflow, which is a previous service that we have launched. You also have choice states where depending on the content of your JSON document in a given state machine at a given point, you can actually branch based on the logic and the values that exist within your JSON. Parallel states allow you to fork and join the data across tasks. And wait states allow you to delay for a specific time. And you'll see wait states come into play in a little bit. We're implementing pollers, and we have wait states in order to make sure that we are not overhammering a given API. You can also introduce failure logic within your state machine should you need to, for example, fail after an error. And you can also have success in pass states as well. So a success state is where you stop an execution successfully as given the name. And a pass state allows you to pass through your input to a given output, which can help with things like debugging, et cetera. So as I mentioned, you build these visual workflows using state types. And let's look at a simple example of what that might be. So let's say you're taking an image. And the first thing that you do from this image is you extract image metadata, and this could be from a Lambda function that is coordinated or correlated with a given task state. You then, based on that metadata, for example, the file type, you check what type of image it is. If it's not supported, you fail your state, or if it is a supported image type, you store the metadata. And from there, you execute two different tasks in parallel. The first thing is you generate a thumbnail image of your original image. And then on the other side, you use, for example, Amazon Recognition to add certain keywords or tags to your individual image. In this case, mountains, people, and snow. And what you can see here from the right, again, is these green paths show you the path that was taken for a given state machine execution. And in this case, you could see it executed successfully. It didn't ever hit the failure state. And with those two concepts in mind, now that we have, sort of step functions that can orchestrate workflows in AWS Batch, which can execute sort of batch tasks at scale, let's take a look at how they sort of interact together and really put this architecture together. So going back to this, you have three fundamental layers. You have the job layer, which you can think of as individual Docker containers that execute a unit of work. They have a set of inputs, they do a process, and they produce a set of outputs. You have AWS Batch, which manages all the resources and scaling of those individual jobs, so things like CPU and memory. And then you have AWS Step Functions that sits on top of that, and you incorporate things like AWS Lambda within your task states, and you implement sort of what we'll show as a long polling mechanism. And then before that, you may be also within Step Functions and Lambda tracking, state and processing time within DynamoDB, say if you're building a multi-tenant architecture. And perhaps you've decided to implement API gateway in front of Step Functions so that you can, serverlessly scale and allow your customers to submit jobs just to an API, and you manage everything on the back end. So you can think of this as a post request that would go through with the original JSON that would be fed into AWS Step Functions. So first, let's take a look at the batch and job state. So executing jobs within this is really, quite simple. As with everything at AWS, our AWS Batch itself is API driven, which means you just need a single function that can really submit a job for you. So beforehand, you specify your Docker run parameters, and you do this within a container overrides portion. You can specify what job queue a job needs to run. And then you submit dependencies. So within AWS Batch itself, Batch does its own dependency management. So you can submit something using the depends on field within the API. But at the same time, you can also manage dependencies outside of that. And here, what we've shown is very simply, if you encapsulated it within a Lambda function, what this might look like. If you imagine you're into the Lambda function, you have the event JSON or the dictionary if you're using Python that contains depends on, overrides, job definitions, etc. You can very simply map that input JSON config into a AWS Batch API call. And from that, you get a response with the job ID, and you can act on that going forward. And with this, there are several specific considerations for the batch layer that I think are important to talk about here. So when you think about AWS Batch and the fact that you can run multiple jobs on the same instance, and that within a batch workflow, in order to really seamlessly scale and have your application be pretty much serverless, you want to not really care about in a lot of cases where an individual job will run. So job one may run on a specific instance, and job two that depended on job one may run on a different instance. And because jobs are managed at the container, not instance level, you cannot necessarily guarantee that consecutive containers in a workflow will run on the same instance. And one of the architectural patterns that we've seen customers use in a lot of cases to sort of bypass this dependency is they use Amazon S3 to stage all of their data, and they read and write everything else from there. And one of the really nice artifacts that falls out from this is that you inherently, by reading and writing all your data from S3, get things like traceability, logging, etc. You can see within each job what the inputs were in S3 and what outputs it wrote. And it gives you this really nice traceability and logging, which we find is an added benefit, for example, in regulated industries. The next thing I want to talk about is multitenancy. And this really gets to the fact that you may have multiple jobs or, in this case, Docker containers that run batch processes on the same instance in the same working directory. If you think about the fact that, let's say you have a large EBS volume as a scratch volume in Genomics, and within this scratch volume, you may have multiple processes that are running on the same instance. And in that case, you want to be sure that you're not overwriting, any, common files or scratch files. So a solution here that we found works very well is you build a lightweight wrapper around your core executable. And within the scratch directory, each batch process, the very first thing it does before it, sort of submits the main executable or process to run, is it creates a subfolder with a unique identifier. And then you pass that subfolder as your sort of new scratch directory, and all scratch data ends up being written to that directory. And what's really nice is the idea of volume reuse just naturally falls out from here. One of the other things that you do need to think about is if you want to reuse instance to optimize for cost and performance, the scratch data really only needs to live as long as the job that's using it. And effectively, after it ends, you want to be able to delete it and reuse that volume space. And if you think about the fact that to start to deal with multi-tenancy, you create this subfolder with a unique identifier, all you have to do at the end is delete that subdirectory, and you've effectively cleaned up and allowed that space to be reused going forward. And what this does is really allow you to minimize or optimize your EBS storage costs or your instance storage costs. And when we look at step functions deployment, what's shown on the left is really our core workhorse. This is an example state machine that is actually available in the console today. If you go to the AWS Step Functions console and actually click on the job poller, it'll put this example state machine up on the left. And what it does is it implements two AWS Lambda blueprints on the right, which we've built, called batch submit job and batch get job. And they're available in both Python and Node.js. But fundamentally what you have here is you first submit a job, and then you do a long poll with the job status where you wait, you query the job status, and AWS Batch may return starting or runnable or running. And if it's anything but failed or succeeded, it'll go back through, it'll poll again, or wait and then poll again. But when your AWS Batch job, and you're querying this again through the describe jobs API within Batch, if it failed, you can error handle with any type of custom logic that you wish to build in with step functions. Or if your job succeeded, you could head to the next job or clean up the job or do whatever you need to do within step functions. And what this gives you is a flexible workflow deployment model. And I think one of the things that's really nice that falls out of this is you're able to decouple your batch engine and your workflow orchestration. So when you think about separation of concerns, this allows you to iterate quicker on the batch side as well as the workflow side, or perhaps have separate teams or separate engineers devoted to each thing, and they can work and know how to interact with each other, but can iterate much more rapidly. One of the other really nice things that falls out is with AWS Batch, you define, your workflow and your job dependencies and your effective DAG as code. Well, now you can actually define it as JSON, which makes it, in a lot of cases, easier to deploy, makes it easier to automate, and easier to test because you're actually testing specific fields. And with that, you can then, in addition to your overall workflow, while many applications within a batch workflow are by nature batch specific, you can integrate non-batch applications as well. And getting to the point of easier to test and be flexible, you can really just change one line or one field to change the entire workflow. So let's say, for example, that you're in Genomics, which is my space, and you have two different tools that you're testing out. Normally you can build and you can code in different workflows for each, but in this case, all you have to do is if you have a Lambda function that submits one tool and a Lambda function that submits another tool, all you do within your state machine is you flip out which tool to run. And then from there, you effectively version that state machine or make a new state machine. And you can very quickly and easily do things like tool sweeps and parameter sweeps, et cetera. And it's really nice and allows you as customers to iterate much more rapidly. And I want to close by sort of showing what this may look like an example. So this is a genomics workflow. And while this state machine may look complex, what you actually, if you take a look, it's really those 4 building blocks that we showed before. And in genomics, this is something, you may get the FASTQ data, sort of the raw data that sits on S3, and through a trigger or an API call, you kick off a process. The very first process traditionally is you take those raw unmapped reads and you align them to a reference. In this case, we call it a reference genome. And from there, you may do 2 things. You may collect quality control metrics, and concurrently, you may want to take the outputs from that alignment step and do what effectively is a signal processing step where you figure out where there are differences compared to the reference. And the last thing that you want to do is a step that is called annotation, where you actually take those resulting variations and ascribe some meaning to them. So while the state machine may look, more complex in nature, fundamentally it's the same core building blocks that are effective in really building out your batch workflow in total. And this is something that, while genomics is the example here, to Jamie's point earlier, it's applicable to any type of industry, whether it's financial services, whether it's media and entertainment, et cetera. This sort of, architectural pattern is able to very quickly and easily be templated out. And with that, on behalf of both of us, I'd like to say thank you for taking the time today. If you're interested in learning more about batch and step functions, we highly recommend you take a look at our service pages and sort of the getting started tutorials there. We actually now added a specific tutorial about how to integrate AWS batch and step functions. And then if you really like to dive deep, based on the architecture presented herein, we've actually open sourced an example of how that might apply in the genomic space. And we're constantly updating this based on the feedback we hear from customers. So, please, we encourage you to take a look at it. We are happy to interact and converse on there and really continue to update this architecture so that it can best serve you in the future. Thank you.
Thanks for all the great questions that you've given us throughout the presentation. I know that we've tried to respond to as many of them as we could while we were presenting, but there's a few more we'd like to respond to as well. So the first question that's come in is, how would I determine the cost of running the solution at scale? Well, I'll start with the batch components to this. Effectively, the cost is the cost of your EC2 compute resources. There's no fee for using AWS Batch. You can keep up to 1 million jobs in your job queues. No cost for creating additional compute environments. It's really just the cost of launching your EC2 instances, along with any network storage or database resources used by your jobs. And AWS Batch can also make it really easy for you to take advantage of low-cost EC2 spot instances with the automated job retry capabilities. That makes EC2 Spot far more accessible to most users. Then beyond the batch components, let's look at the step function side of this architecture. And so for the workflow components, Step Functions provides a really generous free tier, I think offering about 4,000 free state transitions per month, and thereafter only charging 2.5 cents for every 1,000 state transitions. So at the end of the day, not going to cost you much for the orchestration, and it really just comes down to the cost of compute and storage database resources. And then, Aaron, do you want to talk a little bit maybe about tagging and how people can track the cost of running these workloads at scale for longer periods of time?
Yeah, sure, Jamie. So there's a couple ways that you can do this. So the first one is you can define tags within your compute environment. So if you're looking at how much a given compute environment, the total compute resources, you can associate those tags with that specific compute environment, and then match that into billing reports, et cetera. One of the really nice things, and I alluded to this just a little bit in the presentation itself, but if you think about the fact that you have these Lambda functions that are orchestrating and polling your jobs, if you have DynamoDB or another type of database that is effectively tracking where job statuses are, every time you pull the status, if you write it to there, what you can then see is, oh, well, I have these 10 jobs and they're associated with this customer, and I have these 10 jobs and they're associated with this customer, and whether they're internal or external. You can then just run reports across Dynamo or wherever and really get this really nice fine-grained billing. And what's nice is that's just an extra line or two of code that natively falls out of this architecture. So it's a nice, sort of addition that gives you the ability to have this fine-grained billing if you're doing, say, multi-tenant SaaS applications that are built off of this architecture.
Great. Yeah, so the next question actually extends on this. So has the solution been tested at scale? And as I'm talking about this, maybe I'll share a little bit of an anecdote of an AWS Batch user. So we have a few customers that are now starting to run AWS Batch at really significant scale. One in particular who's been running jobs regularly at several tens of thousands of eCPUs at any given moment. And they've implemented exactly the pattern that you just described, Aaron, where they log metadata associated with their jobs and some additional application details to DynamoDB. And then over time, they archive this information to Redshift. So it's effectively free to be able to run these reports and track their usage across the enterprise. And with some of the additional tagging that they're applying to their own jobs, they're actually able to generate reports showing by cost center and by user how much work are they completing and how much are the associated compute resources costing the organization. On the step function side, do you have experience, or maybe in talking with the step functions team, any experience with the scale of work that they're seeing?
Yeah, absolutely. So, step functions, you can manage many sort of concurrent, state transitions. And what, part of this is, right, implementing the appropriate wait conditions that sort of aligns to your specific requirements in terms of, workflow management, et cetera, and how long if your jobs take, for example, several hours to run, you probably don't need to be polling every 30 seconds. But one of the things that we have seen with customers is customers are now managing millions of state transitions each month. So I would say that that's at scale as well.
Yeah. Okay. Next question is, do I have to package my entire application within a container, or are there other options? Well, there's honestly a ton of approaches that you can take. And while many people do prefer to deploy their entire application, all the libraries and config files and binaries within a single container image for a given job, you actually have a number of alternatives. For example, you could upload arbitrary scripts to S3. And use something called a basic fetch and run job that will first retrieve and execute your script. We have actually a blog post on this that Dougal Ballantyne wrote. If you do a search for fetch and run and batch, should be able to find it. What effectively it does is it takes as a parameter the path to your script that's in S3. And if it's in a zip format, if it's been compressed maybe along with some config files and maybe some basic data, as a first step, it'll unzip your archive, and then it'll run the contents of your application within that zip archive. Another approach I've seen people follow is to use EFS. Maybe you'll have a shared file system that has a shared application home, and run your applications referencing that EFS file system as a volume and mount point within your container images. And then maybe one last option that comes to mind. Some customers will use a custom Amazon machine image, or AMI, within their managed AWS Batch compute environments. And in doing so, they can install software that they're frequently running as a file system within the operating system running on their EC2 instance. And then they can reference this file system as yet another mount point within their containers associated with their AWS Batch jobs, giving them the ability to reference any applications that are already installed without having to embed that within their Docker container. So many options, many approaches, and the approach you choose is almost certainly going to be based on the type of work that you're running. Another question, maybe this one's for you, Aaron. Can I use this solution to run HIPAA-compliant workloads?
Yeah, so when AWS Batch, as of August 31st this year, so 2017, became a HIPAA-eligible service under our HIPAA program, which means you can use AWS Batch as part of sort of your core infrastructure to store, process, and transmit PHI.
Okay, great. Yeah, actually, we're really excited to have completed that work, and we're hoping to see even more healthcare and life sciences related workloads running on Batch as a result of that work that Aaron, you really did a fantastic job helping us through that process. So thank you.
Oh, believe me, I did it because I know customers and partners are really looking forward to that. So yeah. I'm really excited to see what comes out of that.
Yeah, and actually speaking of life sciences partners and working on HIPAA-compliant workloads, this next question is a really interesting one. Can your jobs take advantage of GPUs or even FPGAs? And yes, absolutely. We have a lot of customers and partners that are using this solution that we've just described in the webinar to run hardware-accelerated workloads, especially genomics workloads and machine learning pipelines on AWS batches orchestrated by step functions. So in order to do this, you'll need to run these workloads, submitting the accelerated workloads to an AWS batch job queue that's mapped to a compute environment that's restricted to using the accelerated instances that are appropriate for those jobs. So if you have GPU accelerated workloads, maybe you're creating a P2 instance type compute environment that's used to run GPU workloads. Or maybe if you have an FPGA accelerated workload, like some of our genomics partners have, you would create a compute environment that's only launching F1 instances. And then you use CPU as a proxy for the amount of GPU or FPGA resources that are needed. And then when you run your job, you can either submit jobs that use the entire instance in that case, or you can run jobs that will, for example, in the case of GPU workloads, use NVIDIA SMI to query which GPUs are in use, and then pin that job to the quantity of GPUs that that given job needs. And so as long as you're using CPU as a proportional proxy for the accelerators that you need, you're able to easily have batch continue to scale and scale up and down the compute resources, even for accelerated workloads. And then one last thing I'll note on this, for the remainder of your work, for the CPU and memory and network intensive jobs that can take advantage of an optimal batch compute environment, or one that lets batch choose from any of the other CEM or R instance types or many others, batch can easily run a wide range of workloads, CPU, network, or memory-intensive jobs, all within a single compute environment, and have these jobs be submitted to a single job queue. And they can have interdependencies between the accelerated workloads and the standard jobs. I think with that, those are the remainder of the questions that we have time for today. So once again, I'd like to thank you for joining this webinar and for the great questions and for taking the time to learn about this pattern. We look forward to seeing how you use it and hope that you have a wonderful day. Thanks.